Okay, so this should be a relatively short video covering specific charge. Specific charge is just the charge to mass ratio, and this can be of individual particle, such as a proton, neutron, or an electron, but it also can be to do with ions and nuclei. From the definition, we get this equation, which is the charge over the mass, the charge to mass ratio. The charge is given in coulombs, so C, and in the mass you use kilograms. What this means is that specific charge units are coulombs per kilogram, so that's C kilograms to the -1. This is one of the few formula that aren't actually in the formula booklet, and so it's really important you memorize this. Something to note is that this is essentially the opposite of MZ values in chemistry, and so hopefully you won't get confused. And what this means is that a greater specific charge will result in a greater deflection in an electric field, whereas a greater MZ value would result in a smaller deflection in an electric field. In an atom, the electron has the highest specific charge because obviously the neutron has zero charge, but then an electron has the same charge as a proton but a reduced mass. Also, the specific charge of an atom is zero. That's something to remember, and this is quite obvious because the charge of an atom, well, the overall charge is zero, and so 0 divided by anything will equal 0. Something to be careful of is to include all the masses and charges in the calculation of specific charge, and this is particularly relevant for ions and nuclei calculations. It can be quite easy, for instance, to forget the masses of the neutrons. Here I've wrote down an example question, which is asking for the specific charge of the americium 241 nuclei. Sorry about my handwriting, it's not particularly great. So I suggest that you pause the video now and have an attempt at it before I go through the working. Okay, so it's a nuclei, so we don't have to worry about electrons. And so the only place the charge comes from are the protons. And so using the values in the data table, we can say the total charge will be equal to 95, which is the proton number, multiplied by the charge of a proton, which is 1.60 times 10 to the minus 19 coulombs. And then we divide this by the total mass of the nuclei, and that's the nucleon number, which is 241. And we multiply this by the rest mass of protons and neutrons, which are the same. So it's 241 times 1.67 times 10 to the minus 27 kilograms. And if you put that into a calculator, the final result should be 3.78 times 10 to the 7 coulombs per kilogram, remembering to put units at the end. And that's all for this video.